Okay, so we can write 17 base b as 7 plus b. And we can write 97 base b as 7 plus 9b. Now, what this problem is saying, essentially, is that 7 plus b times some number x equals 7 plus 9b. So, we can write 7 plus b x for some number x equals 7 plus 9b. So, distribute the x to get 7x plus bx equals 7 plus 9b. Now, move the 7's and b's over and factor to get 7 times x minus 1 equals b times 9 minus x. Okay, so the problem says that b has to be greater than 9, and for the least value of x, x has to be greater than or equal to 6 at the minimum, and x has to be less than 9. So we essentially only have to test 3 main values for x, which are 7, 6, 7, and 8. And 6 won't work because we'll get a fraction. If we plug in x equals 7, then we get b equals 21, because 7 times 6 is 42, over 2 is 21. So our first value is 21. And then the second value is if we plug in x equals 8, because then we'll get 49, and b is just going to be 49. So the answer to problem 1 is 49 plus 21, which equals 70. Okay, so problem 2. This is a really simple geometry problem. So we're given this triangle, and then we're given some side lengths, and then basically the problem reflects two triangles over, and then it makes these two new triangles. And then we're given the area of a quadrilateral, DFEG, which is 288, and then we're asked to find the area of this weird-looking heptagon. Okay, so the key thing to notice here is that, first of all, since we're reflecting triangles on the same side, they're going to share the same base and the same height. So that means that they're going to have the same area. So for example, triangle ADF and triangle AFM, they share the base DF and FM. Since it's a reflection, both bases are equal. And since they meet at the same common vertex A, both of them have the same area. And we can say the same thing about these two triangles here, this shaded one and this unshaded one. So essentially, the two outside unshaded triangles, so triangle NDB and triangle A, this point M, they're going to be equal to the areas of the unshaded regions in triangle ABC. And so that's just this and this. And then the remaining areas of the heptagon fill in triangle ABC. So our answer is essentially just the area of triangle ABC, which is all we have to find. Okay, so now the problem gives us some side lengths. So what we're mainly going to focus on here is triangle AEG. So let's draw out triangle AEG. And then the problem says that AF equals 13, FG equals 52, and then we're also given EB equals 8, DE equals 16, and AD equals 4. Okay, so the ratio between a triangle, like two triangles in their area, is the square of the ratio of the side lengths. So we can say that the area of triangle AEG is the square of 20 over the total length, which is 28. So 28 squared times the area of triangle ABC. 20 over 28 simplifies to 5 over 7. Square that, we get 25 over 49. So the area of triangle AEG is 25 49ths, the area of triangle ABC. And the area of triangle ADF is basically going to be 1 over 49ths. So we have the area of quadrilateral DFGE is going to be 24 49ths the area of triangle ABC. And the area of triangle ABC is our answer, so that's what we need to find. So now we can just set up a really simple equation. What we have here is the area of ABC times 24 over 49 equals the area of quadrilateral DFGE, which is 288. And so solving this, we get area of triangle ABC equals 288 times 49 over 24, and that gives us our answer of 588. Okay, so problem 3 says the 9 members of a baseball team went to an ice cream parlor, blah blah blah, and then it says each player had a single scoop of chocolate, vanilla, or strawberry, and at least one player chose each flavor. Okay, so this wording is kind of confusing here. They should have clarified this, but what this is saying is that the number of players who chose chocolate, vanilla, and strawberry, each of these, none of them equals 0, so all of them have to be greater than or equal to 1. What I thought this was saying is that one person chose all 3, but that's not what this is saying, so just keep that in mind. The wording is kind of confusing. And okay, so we can set up a really simple equation here. So let the number of people who chose chocolate be C, vanilla be V, and strawberry be S. So we have the condition that C has to be greater than V, which has to be greater than S, and we have C plus V plus S equals 9. Okay, so now it's just like really simple. We can find like the triplets that work for this, such that we have this descending order, and there are actually 3 of those. So the first triplet that works is 6 2 1. The second triplet that works is 5 3 1. And the third triplet that works is 4 3 2. Okay, so now the problem becomes, in how many ways can we assign the 9 players to satisfy these triplet conditions? And so that's basically just going to be a bunch of like choose bashing. So let me first delete this part. Okay, so for the first triplet, 6, 2, 1, we can have 9, choose 6, and then we have 3 players left. So we'll choose 2 of them for vanilla, and then we have 1 player left for strawberry. So that's the number of ways for 6, 2, 1. And then for 5, 3, 1, we can do 9, choose 5, times 4, choose 3. And then for the last triplet, we can do 9, choose 4, times 5, choose 3. Times 2, choose 2, which is just 1. Okay, so now all we have to do is evaluate this, and then we'll get our answer. So let's get rid of all of this. Make this smaller. Okay. So 9, choose 6. That's going to be 9 factorial over 6 factorial times 3 factorial times 3 plus 9 factorial over 5 factorial times 4 factorial. Since 9 choose 5 is the same as 9 choose 4, we can do 4 plus 10. So that gives us 9 times 8 times 7 over 6 times 3, which is over 2, plus 9 times 8 times 7 times 6 over 24 times 14. Okay, so I'll get rid of this part. 9 times 8 is 72. Divide that by 2 is 36, so 36 times 7 plus 9 times 8, which is 72 over 24 is 3, so 3 times 42 times 14. And this is going to be equal to 2016. And so the answer is 2016 mod 1000, which is just 16. Okay, so now for problem number 4. Let's go to problem number 4. Okay, problem number 4. Number of ordered pairs x comma y, where x and y are integers between negative 100 and 100, such that 12x squared minus xy minus 6y squared equals 0. Okay, so when we see problems like this, technically you could use the quadratic formula and then like write x in terms of y and then do some casework with the discriminant, but I feel like that's going to be way too bashy and a bit overkill for a problem like this. What we can instead do is do some factoring, because like equations like these are usually factorable. So we can write 12 as 4 times 3 or 6 times 2. But since we have like this 6 here, I feel like it would make more sense to do a 4 and 3, because if we have a 6 and 2, then I don't think we're going to get a 6y squared from anywhere. So we have a 4x and we have a 3x here. Okay? And so now what do we want to do? So we want to like find out what the y coefficient is going to be. So we can write 6 as like 2 times 3. So let's maybe try, if we wrote a 2 here, then we can still factor this. So let's write a 2 here. So 3x plus 2y. And then we would have to have 4x minus 3y. So does this work? So 12x squared minus 9xy plus 8xy, that gives us the minus xy, minus 6y squared. So yeah, this works. So this is our factored form of this equation. And so that makes things really, really simple now, because we essentially have two cases. Either this part equals 0, this part equals 0, or both x and y equals 0. So technically 3 cases, but mainly 2. Okay, so for case 1, we can have 4x minus 3y equals 0. So let's do case 1, 4x minus 3y equals 0. So let's just start plugging in some numbers x and y and see if we notice a pattern. Right, so what's the least that x can be? X can be 3, and then we can have comma 4. Note that this is negative 100 to 100, so these can be plus and minus, so we can have negative 3, negative 4, or positive 3 and positive 4. So we'll multiply by 2 at the end. Or we can have 6, comma 8, 6, comma 8, etc. And this is going to keep going on and on. Okay, so now the main question becomes, which one, x or y, is going to reach 100 first? Because 100 is our limit. After 100, we have to stop. And the answer is x, because we're skip counting by 4 for x, and we're skip counting by 3 for y. So x is going to reach 100 before y. So if we have, I'm sorry, I got them mixed up. Y is going to reach 100 before x. So if we have y equals 100 here, then what's x going to be? Well, so we're gonna have the difference between here is 1, the difference between here is 2, and etc. 1, 2, 3, and so on. So how do we write that? Well, 4 times 1 is 4, 4 times 2 is 8. So the difference between, so basically what we can do is we can take y and divide it by 4, and that's the difference between y and x. So like 8 divided by 4 is 2, for example, and 8 minus 2 is 6, and that gives us our value for x. So this is just like really smart, because we don't have to plug in our value for y to get to x, even though you easily could. But so you just get 75 from that pattern noticing. And so now the problem becomes number of multiples of 3 from 3 to 75, and that's just going to be 25. And to account for the negative case, we multiply by 2 to get 50. So 50 for case 1. Okay, and so now let's do case 2. Let me just remove this. And so 50 here. And so for case 2, 3x plus 2y equals 0. 3x plus 2y equals 0. So again, let's start plugging in some values for x and y. So again, this is positive or negative, because they can both be positive or negative. So 2, 3, or we can have 4, 6. This is going to go on and on. Which one is going to reach 100 first? Well, that's again going to be y. Y is actually going to reach 99, not 100, because 99 is the closest multiple of 3 to 100. And so the same similar pattern finding we did in the first case. So we're going to divide y by 3, and then that's going to be the difference between y and x. So 6 divided by 3 is 2, and 6 minus 2 is 4. So 99 divided by 3 is 33, and 99 minus 33 is 66. So the problem becomes, the numbers of multiples of 3 from 3 to 99, and that's going to be 33, but we're going to multiply by 2 to account for the negative case, so the answer for this case is 33 times 2, which is 66. So 66 for case 2. And then our final case, which I mentioned previously, is if x and y both equal 0, and so that's just going to be one case. So we have one case in the middle. So the answer is just the sum of 66, 50, and 1, and that gives us our final answer of 117 for problem number 4. Okay, so now let's move on to problem number 5. So problem number 5, we basically have to use the numbers 1 through 8, and we're asked to find the number of integers that use the numbers 1 through 8 that are divisible by 22. Okay, so divisible by 22. 22 is 2 times 11. So this is essentially saying an even multiple of 11. So even multiple of 11. That means that the last digit of whatever number is a multiple of 22 has to either be 8, 6, 4, or 2. And then we also have to have that number to be a multiple of 11. And for a number to be a multiple of 11, like any number A, B, C, D, etc., to be a multiple of 11, the sum of the odd number digits, which are 1, 3, and then we can have E. So like A plus C plus E minus B plus D has to equal 0 or a multiple of 11. So we can say 11x for x is greater than or equal to 0. And this is absolute value, by the way. So the difference between the odd number digits, the sum of the odd number digits and even number digits, is either 0 or a multiple of 11. So that makes things actually a lot easier because now we actually have something to work with and we know like our divisibility rules. So let's write placeholders for the 8 digits of our number. So 1, 2, 3, 4, 5, 6, 7, 8. Now let's call this even number here n. N can be 8, 6, 4, 2. Only those 4. So we're gonna leave that at n. And now, so I mentioned, right, like the sum of the odd number digits, the difference between odd number digits and even number digits has to be a multiple of 11 or 0. So let's call the odd number digits like w through z, so w, x, y, z, and the even number digits a, b, and c. Okay. So now, let's just take one case of n. So there are essentially 4 cases. We can do casework on n. N can be 8, 6, 4, or 2. So let n equal 8. Let n equal 8. Let me make all this smaller. Okay. If we let n equal 8, then what do we have? Well, then we essentially have w plus x plus y plus c, the absolute value of this, minus a plus b plus c plus n, because n is also the even number digit, a plus b plus c plus n equals 11x, where x is greater than or equal to 0. But we also, x can't be like 3 or 4. It can't be like anything too large. Because notice that if we let n equal 8, then the largest possible sum we can form with 4 numbers is 7 plus 6 plus 5 plus 4. And that's going to be equal to exactly 22. And if we have 22 here, then the sum of these numbers would have to be 0, which is impossible. So x can't be more than 1, basically. If x is 2, then it's impossible to get this difference. So this is actually only true for x is either 0 or 1, right? And so now let's actually do some casework here now. So, yeah. So case 1 is x equals 0. Case 1, x equals 0. If x equals 0, then we have a plus b plus c plus n, which is 8. Because we let n equal 8. A plus b plus c plus 8 equals w plus x plus y plus z. Okay, so now what a lot of people do, and like when they see this, is they just start like plugging in random values a, b, c, and w, x, y, z, and hope something works and they see a pattern or anything. But that's going to take way too much time, and we don't have that much time. So what can we do instead? Well, let's set up a system of equations here. So let a plus b plus c be one variable, and w plus x plus y plus z be another variable. Since we know that n equals 8, we know that a plus b plus c plus w plus x plus y plus z equals 28. X plus y plus z equals 28. And why is it 28? Well, it's just the sum of the first 8 numbers minus n, which is 8. So that's 36 minus 8, which is 28. And so now we have a system of equations here. We can solve for a plus b plus c and w plus x plus y plus z. So if we do that, then let's see, what do we get? We got a plus b plus c has to equal 10. And w plus x plus y plus z equals 18. Okay, this makes things so much easier now because we know exactly what sums to look for. And these are the only sums that are going to work. So we know a plus b plus c equals 10, and w plus x plus y plus z equals 18. So now, basically, the number of like ways we have for a, b, c, and w, x, y, z is the number of triples that sum to 10, for a, b, c not equaling 8 and being from 1 to 7. And so what are those triples? Well, it's just really like small bashing. The first one is 2, 3, 5. And the second one is 1, 4, 5. The third one is 1, 3, 6. And the final one is 1, 2, 7. Note that all of these sum to 10, which is what our system said. And if A, B, C equal all of these, then W, X, Y, Z are basically dependent on them. So if A, B, C is this, then W, X, Y, Z has to be, for example, 1, 4, 6, 7. And likewise for all of these. So there are exactly 4 ways, like 4 different ways to have this equation satisfied for x equals 0. So there are 4 ways. There are 4 ways for this to be satisfied. Now, note it's talking about like the number of numbers, right? So the permutations, we also have to consider permutations here. There are 3 factorial ways to permute a, b, and c, and 4 factorial ways to permute w, x, y, and z. So there are a total of 4 times 3 factorial times 4 factorial ways for case 1. Okay, now here's the key. We can only have x equals 0 work. We can't have x equals 1. Why can't we have x equals 1? Well, okay, so we have, in our first case here, we had a plus b plus c plus 8 equals w plus x plus y plus z, right? And we set up our systems of equations, so let me bring this back out here, right? Oh, it's not even going to show. But essentially what we did is we had our systems of equations set up where a plus b plus c plus 8 equals w plus x plus y plus z. And then these two summed to like an even number here. And so if 11 comes into play, then this is going to become 19. This can either be 19 or negative 3, because if we add 11 to this side of the equation, this becomes 19, and if we add an 11 to this side of the equation and rearrange, this becomes negative 3. So both of those are odd, and now a plus b plus c plus w plus x plus y plus z is even, and odd minus even is still going to be an odd number. And so we're going to have 2 times something that has to be an integer equals an odd number. So we're going to get a fraction for a plus b plus c. And so let me show you exactly what I mean. If I have a plus b plus c plus 19, this is a subcase of x equals 1, equals w plus x plus y plus c. And a plus b plus c plus w plus x plus y plus c equals 28, right? Then what do we have? So this sums to 28. Then we have 28 minus a plus b plus c equals a plus b plus c plus 19. So you have 2 times a plus b plus c equals 47. So a plus b plus c is going to be a fraction, and you can't have a fraction with only integers. So the case of x equals 1 is actually never going to work, regardless of what even value of n you choose from. Because if n is an even value, then the sum is always going to be even, and even minus odd is always going to be odd. So you're always going to get a fraction for x equals 1. So actually, for every single even n, there are always only going to be 4 times 3 factorial times 4 factorial ways. And to confirm this is exactly 4 times 3 factorial times 4 factorial, you can do some small bashing for like the different A, B, C triplets, and you'll find that there are always 4 of them for every single case of n. So that's the key pattern to notice here for this problem. Okay, so with that piece of information, this becomes actually really simple. So we had 4 times 3 factorial times 4 factorial ways for n equals 8. But n can be one of 4 different values. Remember, n can be 8, 6, 4, or 2. So we multiply this by 4 again to get 16 times 3 factorial times 4 factorial equals n. This is n. And so the answer is just this minus 2025. And this is equal to 2304. And so 2304 minus 2025 is equal to 279. So 279 is our final answer for problem number 5. Okay. And now comes the final problem for this walkthrough, which is problem number 6. Let me scroll down. So we have an isosceles trapezoid, and there's a circle inscribed in this isosceles trapezoid. I'm gonna very badly try it here, but yeah. Okay. And we have, this is R, let's say this is S, and we have the circle as radius 3, so the height of this trapezoid is automatically going to be 6. And then they give us the area. They give us the area equals 72. So we have base 1 plus base 2 over 2 times height equals 72, which is the area. So R plus S equals 24. Okay, so now what do we do from here? Like, if you kind of get stuck, because you don't really know what to do with R and S. Like, that's great. But how does that give us R squared plus S squared? So this is kind of weird. Well, notice how we have a circle here, and each of these points is tangent to the circle. And note that external tangents to a circle are always equal. So, for example, this is equal to this is equal to this is equal to this, etc., right? So, with that piece of information, and we're also given that this is an isosceles trapezoid, so meaning this tangent plus this tangent equals this tangent plus this tangent. So with that information, we could probably just like do some variables and then figure out all 4 sides of this trapezoid. And from there, we could use Brahmagupta's formula, where it relates the sides of the quadrilateral to the area of the quadrilateral. So let's see, let this external tangent be x, and let this be s minus x. Then this is also going to be x. Let this one be y and r minus y. This is going to be r minus y, and this is going to be s minus x. And this is also going to be y. And since this is isosceles, the sum of this equals the sum of this. So we have x plus y equals r plus s minus x plus y. And so, we know r plus s equals 24, so that means x plus y equals 12. So boom, we have all 4 sides of this trapezoid. We have 12, 12, r, and s. So now, what we can do is we can do Brahmagupta's. And Brahmagupta's formula, by the way, is kind of like Heron's formula, but for quadrilaterals. And it does come very in handy here. Okay, so this is actually a very bashy part of the problem, so I'm just going to kind of go really fast and not really talk about, like, I'm not going to bash it out right here, I'm just going to write the important steps. So Brahmagupta's gives us the semi-perimeter is going to be 12 plus r plus s over 2. And so if we do s minus the first side length, which is r plus s over 2, times r plus s over 2, times 24 minus r plus s over 2. Remember, we subtracted the semi-perimeter from 12 and 12, and now we'll subtract it from r and s. And so then we subtract it again. We subtract it from s here. Oops. And again, they give us that this is equal to 72. Okay, so now what we're going to do is we're going to square both sides, and then kind of simplify and clean things up a bit. And so and also make sure to substitute r plus s equals 24, because that really does come in handy. So substituting r plus s equals 24, and, kind of simplifying this equation a bit, we get 24 squared minus r minus s squared equals 16 times 72 squared over 24 squared, which equals 144. Okay, and so from here, it's basically just like a simple quadratic to solve for r minus s. We find that r minus s is equal to 12 root 3. Okay, boom. Now we have a really easy systems of equations for this problem. And what is that system? Well, we know r plus s equals 24, so let's just write that here. R plus s equals 24. And so now we can easily just solve for r and s. We find that r equals 12 plus 6 root 3. And s equals 12 minus 6 root 3. And so the problem is asking for r squared plus s squared, right? So then we just square both of these and add them up. So we have 12 squared, and then the 2ab squared terms cancel out, right? So we have 12 plus 6 root 3 squared plus 12 minus 6 root 3 squared. So that's just going to be equal to 12 squared times 2 plus 6 root 3 squared times 2. And that gives us 144 plus 72 times 6. I'm pretty sure. Right? Oh wait, no. This is 36 times 3. 36 times 6. So that gives us 288 plus 36 times 6. And that gives us our final answer for this problem of 504. So 504 is the answer to problem number 6. And that's all for this problem 1 through 6 walkthrough. I know I kind of went through the solutions a bit fast, but I hope this video kind of helped you out if you were struggling with understanding some of these solutions. But yeah, thank you for watching, and I hope you enjoyed.